Hi, everyone. My name is Cristina Baglio, and I'm a postdoc at New York University, Abu Dhabi. And today I will talk to you about recent work aimed at unveiling the emission of jets in the Neutron Star X-Ray Binaries SAX J1808. So I don't think we need an introduction about X-ray binaries after the last talks. So very briefly, we typically have a compact object that is a black hole or a neutron star, and a main sequence star that accretes mass onto the compact object through the formation of an accretion disk. And in many cases, we also detect the emission of collimated jets that will be typically dominant in the radio. So in this work, in this presentation, I will talk to you about a transient X-ray binary. So an X-ray binary that displays a short period of outburst with an enhanced activity and longer period of quiescence where the activity is lower and also the flux. So this green spectrum here is the typical spectrum of a jet. So jets emit synchrotron radiation, and their spectrum is flat at the lowest frequencies where the jet is optically thick, and then turns negative at higher frequencies when the jet becomes optically thin. And the turning point is called the jet break frequency, and it is expected to be in the infrared. The problem is that the jet's emission at these frequencies is diluted with the emission from other more dominant components, like, for example, the accretion disk, as you see here. And therefore, if a jet is emitted, we will typically detect an extra red component with respect to the black body tail of the accretion disk. And this red component is called infrared excess. And it is one of the most common signatures of the emission of jets at these frequencies. So moreover, if the system is bright enough, we can also look for linear polarization of the emitted radiation. In fact, synchrotron radiation is known to be intrinsically polarized. And in particular, for X-ray binaries, we do expect to observe a low level of polarization in the radio of a few percent due to cancellation effects that arise in the optically thick jet. In the optical, again, we expect to observe a low level of polarization, this time just because the jet is not dominant in the optical and all the other components are typically unpolarized. And we do expect to observe a bump in polarization in the infrared instead, where the spectrum of the jet is optically thin and also where the accretion disk is not dominant. So, of course, everything will depend a lot on how ordered the magnetic field in the jet is, because if, for example, the magnetic field is strongly tangled, we will have many cancellation effects, and again, the polarization will be low. So we can say that polarization can help a lot investigating the magnetic field in the jet, which is quite an unexplored field, especially for neutron star X-ray binaries. So we decided to try to track the evolution of jets in X-ray binaries using an optical polarimeter, and we chose to study a neutron star X-ray binary for which the coupling between accretion and ejection is still uncertain and has been less investigated so far. So neutron star X-ray binaries are faint, so we applied for time at the VLT, and we got some hours with force 2 to monitor a neutron star X-ray binary outburst. And in August 2019, SAX J1808 went in outburst, and we detected it in the optical thanks to our monitoring with the Las Cumbres Observatory network of telescopes. And you can see here the I-band light curve of the outburst, where we identify a main outburst phase here and then a reflaring phase. And this is a typical behavior of SAX J1808 during outburst. So we triggered the VLT, and we got a lot of epochs that I highlighted here with these numbers. And to extract the polarization level and angle, we selected a group of reference stars that we're supposed to be unpolarized. And as you see here in the P theta diagram, they actually are unpolarized, well, intrinsically unpolarized. And we evaluated this S parameter here, which is basically a projection of the polarization. And by fitting the S parameter with this function using an MCMC algorithm, we got precise estimates of P and theta. So these are the linear polarization level and angle curves that we obtained thanks to our campaign. As you can appreciate in the middle panel here, we have several significant but low detections of linear polarization in all bands, with a maximum polarization of 2.2% here. And I just want to highlight that the significance of these measurements is really excellent for a neutron star X-ray binary, with very small errors and also upper limits that go down to 0.2% in the R band, which I think it's impressive. So of course, it is possible that this low level of polarization is due to synchrotron emission from a jet. And in this case, the almost constant polarization angle that we measure here is indicative of a jet that has a position angle of 120 degrees, but this will have to be confirmed by radio observations, of course. So I add that all the detections that I'm showing here are already corrected for interstellar and instrumental effects. And the interstellar expected polarization is very low according to the Sierkowski law, below 1.5%. A few words about the spectral energy distributions. Here on the left, I reported the SEDs that were built during former outbursts, and you can clearly see that the infrared excess is visible in all of the SEDs, which means that this source really likes to emit jets when it goes in outbursts. And here you can see the same SED that I already showed, together with a compilation of some of the 2019 outburst SEDs in different epochs. And you can see that the SEDs are strongly variable. So we detect the low frequency excess here, but not here, for example, that is the epoch 1, so at the very beginning of the outburst. So this means that the jet is variable and that we can track it also by looking at the SEDs. So to unveil the emission of jets in the system, we built this color magnitude diagram, which is V magnitude versus V minus I color. So basically, the bigger this quantity is, the bigger this quantity is, the redder the spectrum is. And we overplot this black body of an accretion disk model. And also all these numbers indicate the polarization epochs in which we took the data. So we can see different behaviors in this diagram. We have epoch 1, that is at the beginning of the outburst, and it is also one of the closest to the black body model. Here, epoch 2 to 4 that are during the main outburst have the strongest jet contribution. In fact, as you can see, they are far from the model and they are redder and brighter. Here in epochs 5 and 6, during the initial decay, we have less jet contribution, but still the jet is there. In fact, we are still redder and brighter than the disk. And again, here in the reflaring state, we are going back to being consistent with the disk model. So we try to explain our polarization observations in terms of jet emission. And we built this new figure here, where we report the degree of linear polarization against the V minus I jet. That is the V minus I that we measure, so the color that we measure, after the subtraction of the contribution of the jet of the disk to the color. So it is evident that we have a correlation, and in particular that low levels of polarization correspond to a lower contribution from the jet because the spectrum is bluer. And this suggests that the linear polarization that we measure is indeed due to synchrotron emission from the jet. And also the only point that is out of the correlation is this, and it is observed only at low frequency in the I band. So again, this might be a flare in the jet. So if we believe this, the low level of polarization that we detect means that the magnetic fields are very tangled, and we can estimate an ordering level of the magnetic field between 1 and 4%. So these are my conclusions. I might be out of time, so I just want to highlight that it is evident that polarization has a lot to say also for very faint sources like neutron star X-ray binaries. So stay tuned for very exciting results soon. Thank you.